Has it ever struck you in a quiet moment the sheer, staggering improbability of your own existence? You are a conscious being born of stardust and intricate biology, standing on a fragile sphere of rock and water that is hurtling through an infinite silent void. For all of human history, this sphere, our Earth, has been the entirety of our reality. It is the stage upon which every triumph, every tragedy, every love story, and every war has been played out. It is our cosmic anchor, the only home our species has ever known, a vibrant living jewel set against the velvet blackness of space. And yet there is a deep instinctual pull within us, a restless curiosity that has compelled us since we first learned to walk upright to look away from the ground beneath our feet and lift our gaze to the heavens. We have charted the constellations named the wandering stars and woven our most profound myths and aspirations into the celestial tapestry above. The night sky has always been more than just a canopy of distant lights. It has been a mirror reflecting our deepest, most persistent question. A question whispered around ancient campfires and debated in the halls of modern observatories. A question that defines our search for meaning in a universe that appears at first glance to be profoundly empty and indifferent. Are we alone? Is this precious fleeting spark of life on Earth a singular miraculous accident, a lonely cry in an unending cosmic wilderness? Or is it possible that somewhere out there, circling another sun, another world waits, another stage, another beginning, perhaps even another home? This is not merely a philosophical inquiry anymore. It has become the driving force behind one of the greatest scientific odysseys humanity has ever undertaken. We have built colossal eyes of glass and steel instruments of such exquisite sensitivity that they can detect the whisper of a planet from trillions of miles away. We have launched our mechanical emissaries into the solar system and beyond, transforming points of light into worlds we can map and study. For centuries, the thought of finding another Earth was the exclusive domain of fiction, a dream confined to the pages of books and the reels of film. But a revolution has occurred quietly, and then all at once, the dream has begun to bleed into reality. We have discovered that the universe is not empty. It is in fact teeming with planets. Thousands upon thousands of them have been unveiled in just the last few decades, a staggering census of hidden worlds orbiting countless suns. We have found gas giants larger than Jupiter dancing impossibly close to their stars. We have found icy wanderers cast out into interstellar darkness. We have found worlds of crushing gravity and worlds that may be covered entirely in water. Each discovery is a new verse in a cosmic epic we are only just beginning to read. But among this bewildering gallery of alien worlds, one type calls to us with a particular irresistible urgency: the terrestrial rocky planets. Worlds like our own, worlds that might possess the fundamental ingredients for life. And the ultimate prize in this grand celestial treasure hunt is not just any rocky planet, but one that orbits its star within a very special narrow band of space. A region neither too hot nor too cold, where the energy from its sun is just right to permit the most precious substance we know of to exist in its liquid state, water. Astronomers call this the habitable zone, but we might call it the realm of possibility. The discovery of any planet in this zone is cause for celebration. But to find one that is also similar in size to Earth, and to find it not in some distant anonymous corner of the galaxy, but right next door in our own cosmic neighbourhood, that is a discovery that changes everything. It elevates the question from a distant hope to an immediate tangible mystery demanding to be solved. Welcome to the Alpha Centauri system. A trio of stars, our closest stellar neighbours, bound together in a complex gravitational dance. For generations of astronomers, this system has been a beacon of tantalising promise. If another Earth were to exist anywhere, surely the closest possible place would be the first best place to look. For years we searched. We stared intently at the two main stars, Alpha Centauri A and B sun-like twins, that seemed perfect candidates to host a planetary family. But the search proved frustratingly difficult, the gravitational pull of the companion stars making it hard to spot the subtle signs of smaller worlds. The system remained stubbornly silent, a beautiful but apparently barren landscape. But we were looking in the wrong place. The secret was not held by the two brilliant sun-like stars that dominate the system. It was hidden in the faint, almost imperceptible light of the third overlooked member of the trio. A tiny temperamental red dwarf star lurking on the periphery, a celestial outcast named Proxima Centauri. It is the very closest star to our own sun, a mere stone's throw in cosmic terms. So dim it is completely invisible to the naked eye, it glows with less than 1,000th. The brightness of our sun, a flickering crimson lantern in the interstellar dark. For a century after its discovery, it was considered little more than a curiosity. Too small, too feeble, and too volatile to be a likely host for life. But a dedicated team of scientists thought otherwise. They believed that even this faint star deserved a closer look. For years, they monitored it using the European Southern Observatory's most powerful instruments in the barren landscapes of the Chilean desert. They were not looking for a picture. They were searching for something far more subtle, a ghost in the starlight. A tiny rhythmic wobble in the star's motion, an infinitesimal dance caused by the gravitational tug of an unseen orbiting companion. The work was excruciatingly precise, pushing the limits of our technology. They were trying to measure a change in the star's speed of just a few miles per hour, the pace of a person walking from over 4 light-years away. For years, the data was ambiguous, a tantalizing whisper buried in the noise of the star's own turbulent activity. Doubt crept in. Was it a real signal or just a phantom? A ghost created by the star's own magnetic fits? They persisted, gathering more data, refining their techniques, their vigil, stretching across season after season of observation. And then finally the signal emerged from the static, its pattern becoming clearer and more confident with every new measurement. It was undeniable. It was real. Proxima Centauri was not alone. It was wobbling, pulled back and forth by the gravity of an orbiting planet. In 2016, the announcement sent shockwaves through the scientific community and captured the imagination of the world. We had found it, a planet right next door. But it was the nature of this planet that was truly breathtaking. They called it Proxima Centauri b. Its mass was calculated to be just a little larger than Earth's, earning it the designation of a super-Earth, and its orbit, the most critical detail of all, placed it squarely, tantalizingly within its star's habitable zone. A world potentially rocky in the right place and practically on our cosmic doorstep. A distance of 7.5 light-years may sound immense, and it is. A journey there with our current technology would take tens of thousands of years. But in the grand scheme of the Milky Way galaxy, 100,000 light-years across, this is the equivalent of having a mysterious unexplored continent just across a narrow sea. For the first time, we're not just looking at a fuzzy data point in a distant galaxy. We are looking at a specific tangible world. We know its address. We know its year is just 11 Earth days long. We know its weight. We can imagine it. We can almost reach out and touch it. Proxima b represents a monumental shift in our perspective. It has transformed the abstract search for life into a focused investigation. A celestial detective story with a single prime suspect. The discovery has ignited a firestorm of new questions, each one more profound than the last. Could this super-Earth next door truly be a haven? Could it have an atmosphere, clouds, and oceans of liquid water? Could it, against all odds, harbour life? Or is the promise of Proxima b a cruel cosmic mirage, a world that ticks all the right boxes from a distance only to reveal itself upon closer inspection as a sterile, radiation-blasted hellscape? This is the question that haunts us. Could you live there to even begin to answer that we must move beyond the thrill of the discovery and confront the brutal, complex realities of planetary science? We must become forensic investigators of an alien world, gathering every clue, analysing every piece of evidence and piecing together a portrait of a place we have never seen. This documentary is that investigation. We will embark on an unprecedented journey of scientific exploration, travelling 7.5 light-years in our imaginations to stand on the doorstep of this neighbouring world. Together we will dissect every known fact and every plausible theory. We will move beyond the headlines and dive deep into the data, guided by the world's leading experts who are dedicating their lives to unravelling this planet's secrets. We will explore the violent, temperamental nature of its parent star, a red dwarf, whose unpredictable fury may be the single greatest obstacle to life. We will analyse the planet's precarious gravitational situation, a world locked in a tight synchronous orbit, forever presenting one face to its star's heat and casting the other into eternal frozen darkness. We will model its potential atmosphere, asking whether a protective magnetic shield could exist to fend off the stellar onslaught, and whether the delicate gases needed for life could possibly cling to its surface. We will build this world from the ground up, simulating its geology, its climate and its potential for water, painting a scientifically grounded picture of what it might actually be like to stand on its surface and look up at a sky dominated by a vast smouldering red sun. This is a story of immense hope and profound challenge, a story that pits the tantalizing possibility of a second Earth against the harsh and unforgiving laws of astrophysics. The stakes could not be higher. Finding a habitable world so close would not just be another scientific discovery. It would fundamentally reframe humanity's place in the universe. It would change how we see ourselves, our future, and our destiny among the stars. It would be a sign that we are not a cosmic anomaly, but part of a larger living universe rich with possibilities. So the journey begins now. We have our destination. We have our mission. The first step in any planetary investigation is not to look at the planet itself, but at the powerhouse that gives it life and light the star it calls home. Our forensic examination of Proxima Centauri b must therefore start with a thorough understanding of its volatile and enigmatic sun. For the fate of this world, its potential for life, or its condemnation to sterility was written in the fires of its star. The story of Proxima b is inextricably bound to the story of Proxima Centauri, and it is there in the heart of that flickering crimson furnace that our search for answers must begin. What if the most profound discovery in human history was not the invention of something new, but the stunning confirmation of an idea whispered in secret for millennia? An idea so dangerous, so contrary to the established order, that to even speak of it was to risk everything. In the year 1600, on a cold stone piazza in Rome, the philosopher Giordano Bruno was burned alive. His crime was not merely challenging the authority of the church. His true heresy was a crime of imagination. He dared to look at the pinpricks of light in the night sky and see them not as divine decorations, but as other suns. And around those suns he envisioned an infinity of other worlds teeming with other lives. For this cosmic vision, he was silenced by fire. Yet an idea once spoken can never be truly extinguished. It became a ghost that haunted the corridors of science for the next 400 years. This grand, beautiful and terrifying possibility that we are not alone, that Earth is not the sole crucible of existence, became the silent engine of astronomy. It drove us to build larger and larger telescopes, magnificent cathedrals of glass and steel, all designed to sharpen our vision, to peel back the layers of the cosmos, and find a reflection of ourselves somewhere in the crushing darkness. We were searching for a cosmic sibling, a celestial echo of our own world. But this profound dream slammed headfirst into a wall of cold, hard physics. The universe we discovered is a masterpiece of scale, and we are infinitesimally small. The stars which appear to us as tranquil points of light are in fact raging thermonuclear furnaces billions of times brighter than any planet that might orbit them. Trying to spot an Earth-like world next to its star was like trying to see a firefly hovering next to a searchlight from thousands of miles away. It was a task beyond the reach of any technology we could conceive. The universe remained silent, its sheer vastness a seeming rebuttal to our hopes. The grand silence felt mocking, a declaration that we were perhaps a magnificent accident, a lonely island of life in an endless, sterile ocean. For centuries, the search for other worlds was relegated to the realm of philosophy and fiction. It was a beautiful thought, but not serious science. How could you prove the existence of something you could never hope to see? The challenge seemed insurmountable, the problem fundamentally unsolvable. We were cosmic castaways trapped by the tyranny of distance and the physics of light. Any traveller orbiting another star would be utterly invisible to us, a ghost in the machine of the cosmos, forever beyond our perception. The great quest had stalled. Bruno's dream was fading back into myth. Then, in the latter half of the 20th century, a subtle, revolutionary idea began to take shape. It was a stroke of genius born from utter necessity, a pivot in thinking that would change everything. If we couldn't see the planet, the scientists reasoned perhaps we could see its effect on its star. Perhaps the ghost in its passage would leave a trace. They realised that a star and its planets are not a static arrangement of a massive object with tiny companions. Instead, they are partners in a delicate and perpetual gravitational waltz. While the star's gravity is undeniably the dominant force holding its worlds in orbit, every planet, no matter how small, exerts its own tiny persistent gravitational pull back on the star. Imagine a hammer thrower spinning in a circle. The athlete is immense, the hammer small. But to keep the hammer swinging, the athlete cannot stand perfectly still. They must lean back, shifting their own centre of mass to counterbalance the weight they are swinging. They wobble. A star in exactly the same way doesn't sit perfectly still at the centre of its solar system. It is constantly being tugged, pulled and nudged by the worlds that circle it. It performs a miniature complex orbit of its own around a common centre of mass. It wobbles. This stellar wobble was the secret, the cosmic clue we had been missing. It was an impossibly subtle movement, a motion so small that from light years away it would be utterly undetectable to the human eye or a photographic plate. But we didn't have to see the wobble, we just had to measure it. And for that we would need to learn how to dissect starlight itself with a precision previously thought impossible. The technique that emerged is one of the most elegant in all of science, the radial velocity method. It is the art of listening to a star's song. Every star broadcasts its light across the cosmos, and embedded within that light like a secret code is a spectrum, a rainbow fingerprint that reveals its chemical makeup, its temperature, and most critically its motion. As a star moves through space, the light waves it emits are compressed or stretched, a phenomenon you experience every day as the Doppler effect. Think of the siren of a passing ambulance. Its pitch rises as it races towards you and falls as it speeds away. The sound waves are being squeezed together, then pulled apart. Light behaves in precisely the same way. If a star in its tiny orbital wobble is moving slightly towards Earth, the waves of its light are compressed. The entire spectrum of the star shifts infinitesimally towards the blue end. When it wobbles away from us, the light waves are stretched and its spectrum shifts minutely towards the red. A blue shift, then a red shift. A blue shift, then a red shift. It's a cosmic metronome, the steady rhythm of an unseen world's passage. By measuring these cyclical, almost imperceptible shifts in a star's light, we could infer the presence of an invisible companion. We could determine the ghost's mass, calculate the length of its year. We were no longer looking for a planet. We were looking for its gravitational shadow, its whisper carried on a river of light across interstellar space. To achieve this required instruments of breathtaking sensitivity. We had to build spectrographs of unprecedented stability machines, housed in vacuum-sealed, temperature-controlled chambers, isolated from the slightest terrestrial vibration from a passing truck or a distant earthquake. These instruments, like the high-accuracy radial velocity planet searcher or HARPS at the La Silla Observatory in Chile, became our celestial seismographs. They could measure a star's velocity, its wobble towards or away from us, with a precision of 1 meter per second. That is the speed of a gentle walking pace. From trillions of miles away, we had learned to detect a star moving as slowly as you stroll through a park. The stage was set for a revolution, and in 1995 the revolution arrived. Two Swiss astronomers, Michel Mayer and Didier Queloz, were monitoring the star 51 Pegasi, a sun-like star 50 light-years away. They were not expecting to find anything remarkable. The prevailing wisdom was that if other solar systems existed, they would probably resemble our own, with small rocky planets close in and gas giants far out. Any wobble from a distant Jupiter-like planet would take a decade or more to complete one cycle, requiring immense patience to confirm. But what they found was not patient. It was immediate, and it was utterly bizarre. The data screamed from their computer screens. 51 Pegasi was wobbling and wobbling violently with a frantic, impossibly short period of just over 4 days. The only explanation was a planet of immense size, at least half the mass of our own Jupiter, orbiting its star in a blisteringly tight embrace far closer than Mercury orbits our Sun. It was a world from science fiction, a hot Jupiter, a gas giant roasted by its parent star to thousands of degrees. The discovery was so strange, so contrary to every model of planet formation we had, that at first the scientific community was skeptical. It seemed impossible. But the data was undeniable. The ghost had been found. 51 Pegasi b was the first confirmed exoplanet orbiting a Sun-like star, and its discovery threw open the floodgates. It was the shot heard round the world, a moment that transformed exoplanet hunting from a fringe pursuit into the forefront of modern astronomy. Suddenly we had the tools, we had the proof of concept, and we turned those tools everywhere. The Kepler Space Telescope, using a different but complementary method, would go on to find thousands of candidate worlds, revealing a stunning truth. Planets are not the exception in our galaxy. They are the rule. Almost every star you see in the night sky is likely to have a planetary system. We found super-Earths, mini-Neptunes, worlds of water, worlds of lava planets orbiting two suns like Tatooine. The cosmic menagerie was more diverse and more wonderful than Giordano Bruno could have ever dreamed. The galaxy, it turned out, was teeming with worlds. Yet amid this deluge of discovery, one question remained hanging in the star-filled darkness. We had found thousands of planets, but they were all so far away, hundreds, even thousands of light-years distant. They were statistical certainties, fascinating case studies, but they were not neighbours. They were abstractions too remote to ever visit, too faint to ever truly characterise. The deepest, most human desire was not just to know that other worlds exist, but to find one that was close. A world we could study in detail, a world that we might in some distant future even reach. Where was our nearest exoplanet? The attention of the world's astronomers began to focus with a new and determined intensity on a single point of light, one so faint it is invisible to the naked eye. A star that is in cosmic terms right on our doorstep. Proxima Centauri, the closest star to our Sun. It's a tiny, ill-tempered red dwarf, a celestial ember just over 4 light-years away. Compared to our Sun, it is a pale, cool shadow, possessing only a fraction of its mass and a sliver of its brightness. For decades, it was largely ignored in the search for life. Red dwarfs were considered too volatile, too dim their habitable zones. The narrow orbital band where liquid water could exist too cramped and close to the star's dangerous radiation. But its proximity made it an irresistible target. If there was a planet there, it would be the most important world ever discovered beyond our solar system. The European Southern Observatory launched an ambitious campaign with a fitting name, the Pale Red Dot. It was a deliberate echo of Carl Sagan's famous pale blue dot photograph of Earth, a search for a similar oasis of possibility around our nearest stellar neighbour. Using the HARP spectrograph, the same type of instrument that had found 51 Pegasi b, an international team of astronomers began a painstaking vigil. They would stare at this one dim red star night after night for months. They were looking for a wobble, but this time they weren't searching for the frantic tug of a hot Jupiter. They were searching for the gossamer fine pull of a small rocky world, a planet perhaps the size of Earth. The signal, if it existed at all, would be buried deep within the noise of the star's own turbulent activity. Red dwarfs are notorious for their violent stellar flares and churning surfaces, all of which can mimic the very Doppler shift signal the astronomers were trying to find. It was like trying to hear a single pure note in the middle of a raging storm. The challenge was immense. Every photon of light from Proxima Centauri was captured, dissected, and analysed. The data accumulated slowly, meticulously. For 2 years, the team gathered observations. They wrestled with the star's intrinsic noise, developing sophisticated new techniques to filter out the star's natural volatility from any potential planetary signal. They were searching for a pattern, a faint, repeating rhythm in the chaos. And then, deep within the torrent of data, they saw it. A whisper. A tiny periodic signal repeating with clockwork precision every 11.2 days. It was a wobble so small it was almost lost a velocity shift of just over 1 meter per second. The gentle, walking pace. The gravitational signature of an unseen world tirelessly circling its dim red sun. The calculations were checked, rechecked, and checked again by independent teams. Every other possibility was systematically ruled out. It wasn't the star's rotation, it wasn't stellar activity. it was a planet. On August 24, 2016, the announcement was made and the world was electrified. We had found it, a planet with a minimum mass just 1.3 times that of Earth, orbiting Proxima Centauri. They named it Proxima Centauri b, and it wasn't just a rocky Earth-sized planet. The most stunning part of the discovery was where it was located. Its 11-day orbit placed it squarely, tantalizingly, within the star's habitable zone. It was the discovery of a lifetime, the culmination of a 400-year-old dream. We had found a potential second Earth, a pale red dot circling the very next star in the galaxy. It was no longer an abstraction, it was a destination. A world just 7.5 light-years away, a stone's throw in cosmic terms, a place that shifted in a single moment from the realm of science fiction into a tangible object of scientific inquiry. The news ignited a global sensation, capturing the imagination of millions. For the first time, when you looked up into the night sky towards the constellation of Centaurus, you knew. You knew that right there, just beyond the reach of your unaided eye, was another world, potentially rocky, potentially temperate, potentially bearing liquid water on its surface. We had found humanity's closest cosmic address. But finding a world and understanding it are two vastly different things. This initial discovery was just the first step on a journey that would prove to be far more complex and dangerous than anyone imagined. For this newborn planet, orbiting so close to its volatile red parent, exists in an environment utterly alien to our own. It is a world of perpetual twilight bathed in a crimson glow, a place where the definition of habitable would be tested to its absolute limit. Now that we have found our neighbour, the real exploration can begin. The urgent question is no longer, is there a world, but what is that world? And so, with our telescopes and our dreams aimed at that single tantalizing point of light, we'd found it. A world next door, wrapped in the warm embrace of its star's habitable zone. The initial models painted a breathtaking picture, a canvas of possibility showing deep oceans, stable continents, and perhaps, just perhaps, a sky you could recognize. It was a discovery that seemed to rewrite our place in the cosmos, shortening the immense loneliness of the universe to a mere 7.5 light-years. For a fleeting moment in our history, Proxima Centauri b was not just a planet. It was a promise, a destination, a future echo of Earth. But the universe rarely deals in simple promises. It deals in complexities, in violent truths hidden within the beautiful equations. As we moved past the initial euphoria and began to scrutinize the system, not just with hope, but with cold, hard physics, we were forced to look away from the planet and confront the nature of its parent. We had to stare into the heart of the Proxima Centauri system, and what we found looking back was not the gentle, life-giving gaze of a star like our own sun. It was the smouldering, capricious eye of a red dwarf. This is the central, unavoidable paradox of our nearest cosmic neighbour. The very reason Proxima b can host liquid water, its incredibly tight orbit, is the same reason it may be one of the most dangerous places in the galaxy. To understand this danger, you must first understand the star itself. Proxima Centauri is ancient and diminutive, a mere ember compared to the bonfire of our Sun. It possesses only about 12% of the Sun's mass and shines with less than 0.1% of its luminosity. If you were to swap our Sun for Proxima Centauri, Earth would become a frozen, lifeless ball of ice, its oceans locked solid to the core. For Proxima b to feel the warmth necessary for liquid water, it has to huddle incredibly close, completing a full orbit in just 11 Earth days. Its year is less than 2 of our weeks. This proximity, a mere 5% of the distance between Earth and our Sun, places it directly in the line of fire. Because this tiny dim star is anything but peaceful. It is a flare star, a celestial dragon, prone to violent, unpredictable tantrums of magnetic fury. Our Sun has flares, of course. We see their effects in the shimmering aurorae that dance over our poles, and on rare occasions in disruptions to our power grids and communication satellites. But the flares erupting from Proxima Centauri are a different beast entirely. They are not exceptions to the norm, they are the snorm. On an almost daily basis, this star can suddenly, without warning, double, triple, or even quadruple its brightness across the entire electromagnetic spectrum. In 2017, astronomers witnessed a superflare from Proxima Centauri that caused it to brighten by a factor of 1,000 in just 10 seconds. Imagine for a moment standing on the surface of Proxima b. 1 minute you're bathed in the dim reddish twilight of a calm stellar morning. The next, the sky ignites with a celestial blowtorch. An apocalyptic flash of X-rays and gamma rays 1,000 times more intense than anything our sun produces scours the entire planet. This isn't just a light show. It is an extinction-level event delivered on a weekly or even daily basis. This relentless bombardment of high-energy radiation presents the first great filter for life. The X-ray flux during one of these superflares would be hundreds, if not thousands of times the lethal dose for a human being. Any life on the surface would be sterilized almost instantly. Complex organic molecules, the delicate scaffolding of biology, would be torn apart, their chemical bonds shattered by the sheer energy of the incoming photons. But the danger doesn't end when the flash subsides. Accompanying these flares is a ferocious storm of charged particles, a supercharged stellar wind that slams into the planet at nearly the speed of light. This is not a gentle breeze, it is a cosmic sandblaster. This constant high-energy particle storm poses a more insidious long-term threat. It has the power to strip a planet of its most precious resources, its water and its air. Over millions of years, this solar wind can literally sputter away an atmosphere particle by particle, like a chisel chipping away at stone. It can break apart water molecules in the upper atmosphere, with the lightweight hydrogen atoms escaping into space, forever bleeding the planet dry over geological timescales. A world that may have been born wet could be rendered an arid, airless desert by the incessant fury of its own sun. To survive this onslaught, Proxima b would need a shield, a planetary suit of armour. It would require a global magnetic field far more powerful than Earth's. Our magnetosphere, generated by the churning liquid iron in our planet's core, is our silent guardian. It deflects the worst of our sun's solar wind, channeling the deadly particles towards the poles and creating the very aurorae we admire. For Proxima b to have any chance, its magnetic field would need to be a veritable fortress, a bastion capable of withstanding energies we can barely comprehend. Whether it has such a field is one of the most fiercely debated questions in exoplanetary science. As a super-Earth, its larger size and potentially greater iron core could in theory generate a supermagnetosphere. But its slow rotation, another consequence of its proximity to the star, might work against it, potentially leaving its internal dynamo sluggish and weak. Without that magnetic shield, the planet is naked before the storm, its atmosphere, and any hope for surface life left utterly defenseless. Yet even if we imagine a magnetic field strong enough to fend off the stellar flares, Proxima b faces another more subtle but equally profound challenge. It is a prisoner of gravity, locked in a permanent silent dance with its star. Just as our moon always shows the same face to Earth, Proxima b is almost certainly tidally locked to Proxima Centauri. This gravitational handshake, forged by the immense pull of the star at such a close distance, has arrested the planet's rotation. One hemisphere is trapped in eternal daylight, forever facing the star. The other is cast in perpetual night, a realm of unending frozen darkness. This creates a world of savage extremes that defies our earthbound intuition. On the day side, the constant unblinking glare of the star, however dim, would bake the surface for billions of years. Any water there would have long since boiled away, leaving a scorched, desiccated landscape under a reddish sky. On the night side, without any sunlight to warm it, temperatures would plummet to hundreds of degrees below zero. Any atmosphere would freeze solid, snowing down to form vast glaciers of nitrogen and carbon dioxide on a surface locked in absolute cold. Life as we know it could not exist in these two zones. One is an oven, the other a deep freeze. But this bizarre configuration offers a tantalizing if fragile compromise, the Terminator Zone. This is the twilight ring, the permanent border between day and night, where the star would hang forever on the horizon, casting long, dramatic shadows across the landscape. In this sliver of perpetual dawn or dusk, temperatures could be just right. Not too hot, not too cold. It is here, in this thin circumnavigation of the planet, that liquid water might persist in rivers and lakes. It is here that the dream of a habitable Proxima b makes its last stand. You can imagine a world where all life is confined to this narrow strip of land where evolution unfolds under a sky forever caught in a state of sunset. A world where day and night are not measures of time but are actual places you could travel to. It is a stunning poetic concept, but even this oasis of twilight is fraught with peril. The extreme temperature difference between the baked day side and the frozen night side would create an atmospheric engine of unimaginable power. The hot air rising from the sun-facing hemisphere and the cold air sinking on the dark side would generate winds of cataclysmic force. These would not be gentle breezes. We are talking about permanent planet-circling hurricanes, supersonic winds that would scour the Terminator zone relentlessly. Any life-seeking refuge in this twilight realm would have to endure a never-ending tempest, a physical assault that would make Earth's most violent storm seem like a summer shower. Could complex ecosystems ever arise in such a chaotic environment? Could any organism evolve to withstand such a constant ferocious gale? Furthermore, any atmosphere on a tidally locked planet faces a grave danger: atmospheric collapse. The profound cold of the night side could act as a giant trap, freezing the gases out of the air and depositing them as ice on the surface until the entire atmosphere has migrated to the dark side and the planet is left a barren vacuum. For Proxima b to avoid this fate, it would need an atmosphere thick enough to transport heat efficiently from the day side to the night side, creating a more balanced global climate. It would need to be substantially thicker than Earth's, perhaps more like Venus's, but without the runaway greenhouse effect. So we are left with a cascade of devastating challenges, each one chipping away at the initial beautiful vision of a habitable world. A star that bombards it with sterilizing radiation, a relentless solar wind that seeks to strip away its air and water, a gravitational lock that creates a planet of brutal, uninhabitable extremes. These are not minor inconveniences, they are fundamental existential threats to the very concept of habitability. The scientific community, once united in excitement, is now fractured by intense debate. One camp, armed with the brutal data from the star's flare activity, argues that Proxima b is for all intents and purposes a dead world. A sterilized, airless rock that may have had a fleeting chance at life billions of years ago, but has since been scoured clean by its violent parent. They point to the sheer energetic impossibility of life surviving such a continuous cosmic assault. In their models, the planet is a tragic monument to a failed experiment in habitability, a testament to the fact that simply being in the right place is not enough. On the other side of the debate are the optimists, the dreamers, the scientists who argue that we should not be so quick to impose our own terrestrial biases on an alien world. They counter that we are underestimating nature's tenacity. Perhaps they suggest the planet was born with an immense reservoir of water, so much that even billions of years of atmospheric stripping has not been enough to dry it out. Perhaps it possesses an incredibly dense atmosphere, a gaseous shield that can absorb the radiation and distribute the heat, mitigating both the flares and the effects of tidal locking. They propose that life might not be on the surface at all. It could be thriving deep beneath the planet's oceans, using the water as a protective blanket against the X-ray flashes from above. In this scenario, the ocean's surface might be a violent, churning hellscape, but just a few dozen meters down, a calm, stable environment could persist, warmed by hydrothermal vents on the seafloor. Or perhaps life has retreated underground, becoming a subterranean biosphere completely shielded from the horrors of the sky. In these hidden realms, the violence of the star would be irrelevant. This is the great scientific drama playing out today. We have a suspect Proxima Centauri b and a mountain of circumstantial evidence suggesting it is uninhabitable. The prosecution lays out a damning case: the flares are the weapon, the radiation is the poison, and tidal locking is the prison. Every piece of data we gather about the star seems to add another nail to the coffin of habitability. The defense, however, pleads that we have not yet seen the planet itself. We have only judged it by the company it keeps. They argue for unknown mitigating circumstances, a powerful magnetic field, a thick atmosphere, a deep ocean, a subterranean refuge. They remind us that life is resilient, adaptable, and has a history of appearing in places we once deemed impossible. The truth is, we do not have the final answer. We are like detectives who have arrived at a crime scene, but the main door is locked. All we can do is peer through the windows trying to piece together the story from the flashes of light and the shadows we see moving inside. Is Proxima Centauri b a cosmic tragedy, a paradise lost? Or is it a fortress world, a planet whose life has been forged in fire and tempest, making it far tougher and more resourceful than we can possibly imagine? To find out, we have to find a way to kick down that door. We have to find a way to see the planet not as a shadow but as a world. And so the portrait of Proxima b seemed complete, a world condemned by its own parent star. We had painted a bleak masterpiece of cosmic misfortune, a planet seared by a relentless, unblinking gaze on one side, and frozen into eternal crystalline stillness on the other. A world scoured by stellar winds, blasted by radiation storms 100 times more powerful than any our own sun has ever produced. The initial thrill of discovery, that tantalizing whisper of a neighbor just across the street, had faded into a somber realization. The verdict appeared to be in. Proxima b was a paradise lost, a dream of a habitable world that had died before it could ever truly live. It was a tomb, not a cradle. But in science, a portrait is never truly finished. It is merely a sketch, a momentary interpretation waiting for a new piece of data, a fresh perspective to emerge from the darkness and transform the entire picture. Just as our telescopes were closing the case, another set of instruments began to open it wide again. Not telescopes of glass and steel, but instruments of pure logic running inside the silent, flickering hearts of the world's most powerful supercomputers. These were the crucibles of digital creation, where entire worlds could be born, evolve and die in a matter of hours. And it was inside these virtual universes that Proxima b was about to be resurrected. The problem, the core of our pessimism, had always been the atmosphere. The old models were brutal and unforgiving. They showed that any significant atmosphere would be frozen out on the dark side, its gases condensing into a vast permanent glacier of nitrogen and carbon dioxide snow. The day side, stripped of its protective blanket, would be left naked to the star's fury, its surface water boiled away into the vacuum of space. The planet would become a two-faced monster, a sphere of fire and ice with no middle ground for life. But these models, we were beginning to realize, were perhaps too simple. They were built on our own experience on planets that spin. Proxima b does not spin. It is locked in a gravitational dance, and that changes everything. A new generation of planetary scientists armed with far more complex climate simulations began to ask a different question. What if the atmosphere was not a fragile liability, but a tenacious, self-regulating machine? What if instead of collapsing, it fought back? They fed the computers new variables, a much thicker atmosphere, perhaps 3, 5, even 10 times the mass of Earth's rich in greenhouse gases. A world born with a deeper well of volatile compounds. What they saw emerge from the churning data was not the expected barren rock, but something dynamic, something utterly alien, and something unexpectedly hopeful. Imagine a planetary scale engine, one that never ever shuts down. On the substellar point, the surface directly facing the star Proxima Centauri's light is a permanent blowtorch. The atmosphere there doesn't just warm, it boils. It swells upwards in colossal continent-sized plumes of superheated gas. In the older models, this was the end of the story. But in these new, sophisticated simulations, this upward surge creates an immense pressure differential. High pressure on the day side, low pressure on the night, and nature, as it always does, abhors a vacuum. The result is wind, not wind as we know it. Not a gentle breeze or a seasonal gale, but a perpetual planet-girdling hurricane. A river of air thousands of miles wide, screaming from the blistering heat of the day side into the profound cold of the night. These are winds that would rip the skin from your bones, howling at hundreds of miles per hour, day after day, century after century. A permanent roaring transfer of energy. This titanic atmospheric conveyor belt acts as a planetary circulatory system. It drags heat from the furnace of the day side and distributes it into the frozen expanse of the night, preventing the atmosphere from freezing out and collapsing. It is a world of eternal storms, a place where the sky is never calm. But within this violence there is a seed of salvation. The simulations revealed something beautiful. As that superheated, moisture-laden air from the day side rushes towards the twilight zone, that permanent terminator ring between day and night, it begins to cool. And as it cools, it would condense. This process would form clouds. Not the fluffy fair-weather clouds of Earth, but a vast, thick and highly reflective bank of cloud cover perpetually parked in the skies of the day side. Think of it as a planetary parasol, a natural self-forming shield. These clouds, potentially made of water ice or other reflective compounds, would bounce a significant portion of the incoming stellar radiation right back into space. They would moderate the brutal surface temperatures, turning a scorched wasteland into something more akin to a sweltering overcast tropical day. The terminator zone itself, that ring of endless twilight, transforms in these models from a razor's edge into the most compelling real estate in the system. Here, the winds would be ferocious, but the light would be gentle. The star would hang forever on the horizon, a swollen crimson orb that never sets and never rises. Temperatures might be stable, perhaps even clement. Water carried by the atmospheric river could potentially exist here in its liquid form, tracing silver ribbons across a landscape of perpetual dawn or dusk. You're standing in a world where the concept of a day has no meaning, where your entire existence is lived in a single unchanging moment of sunrise. The winds would be your constant companion, the roaring soundtrack to a world held in a delicate storm-driven equilibrium. Suddenly, the tidal lock wasn't just a curse. It was the very engine driving a climate system that could against all odds make the planet's surface survivable. Yet even with a stable atmosphere, a world so close to an angry red dwarf faces another mortal threat: radiation. Proxima Centauri's flares are terrifyingly powerful, unleashing torrents of high-energy particles capable of sterilizing a planet's surface and stripping away its atmosphere over millions of years. For life to have a chance, it needs more than clouds. It needs a shield. It needs a magnetic field. And for a tidally locked planet, this presented a profound cosmic puzzle. On Earth, our protective magnetosphere is generated by the geodynamo in our core. The rapid spin of our planet churns a vast ocean of liquid iron, creating powerful electrical currents that in turn generate the magnetic shield that envelops our world. It deflects the solar wind and catches the most dangerous cosmic rays. Without it, our atmosphere would have been blasted away eons ago and the surface would be as sterile as the moon's. But Proxima b barely rotates. Its day is the same length as its year. How could a world with such a sluggish, almost imperceptible spin generate the kind of dynamo needed for protection? The initial assumption was that it couldn't. It was another check in the box for a dead world. This is where planetary modelling took another leap into the unknown, exploring the hidden forces at work inside an alien world. The key theorists proposed might not be rotation, but the very same gravitational forces that lock the planet in the first place. The relentless tidal pull from Proxima Centauri doesn't just hold the planet in its grip, it constantly squeezes and stretches it. The planet's solid crust and mantle would bulge slightly, deforming under the strain. But deep inside, if Proxima b possesses a large liquid metallic core, these same forces would stir it into motion. Imagine holding a spherical water balloon and rhythmically squeezing it. The water inside would slosh and churn. Now scale that up to the size of a planet with a core of molten iron being rhythmically kneaded by the gravity of its star. These tidal forces could drive powerful convective flows within the liquid core flows that are complex and turbulent. And where you have the motion of a conductive fluid, you have the potential for a dynamo. It wouldn't be like Earth's. It might be weaker, perhaps more chaotic, with poles that wander unpredictably. But it could be strong enough. It could be the magnetic umbrella the planet desperately needs. In a stunning piece of theoretical work, teams began to simulate the interior of a tidally stressed super-Earth. The results were startling. Depending on the size and composition of its core and the precise eccentricity of its orbit, Proxima b could indeed generate a self-sustaining magnetic field. A gravitational gyroscope spun not by planetary rotation, but by the constant rhythmic breath of its star's gravity. The very force of its confinement could be the source of its protection. This magnetic shield would be the planet's first and most critical line of defense. When a flare erupted from Proxima Centauri, this invisible barrier would flare to life, catching the torrent of charged particles and funneling them away from the planet, creating spectacular permanent auroras in the skies above the dark side. An endless silent light show playing out over a world that never sees its star. The existence of such a shield changes the calculus of habitability completely. It means an atmosphere once formed could be retained for billions of years. It means the surface radiation, while still intense during a flare, would be survivable. The pieces were beginning to fit together. A thick atmosphere regulated by terminator winds and shielded by reflective clouds, all protected by a tidally generated magnetic field. The bleak portrait was being painted over with vibrant, hopeful colours. But what if the surface for all these defences was still too hostile? What if the answer to life on Proxima b lay not on its stormy surface but deep beneath it? This led to the boldest and most profound hypothesis of all the possibility of a subsurface ocean. The idea is born from observing moons in our own solar system like Jupiter's Europa or Saturn's Enceladus. These are ice worlds far from the sun's warmth, yet they hide vast global oceans of liquid water beneath their frozen shells. The secret to their warmth is not sunlight but tidal heating. The immense gravity of their host planets constantly flexes and kneads their interiors, generating enormous frictional heat that keeps the water below liquid. Proxima b is in an even more extreme tidal environment. It is being squeezed and stretched by its star with immense force. Even if the surface facing the star is warm and the surface facing away is frozen solid, the tidal friction deep within its mantle could be generating a colossal amount of geothermal energy. Let's imagine this scenario. The surface of Proxima b is an inhospitable wasteland. The day side is too hot and irradiated. The night side is a cryo-hell, a landscape of nitrogen ice colder than Antarctica. But beneath that frozen night-side crust, perhaps miles down, lies the greatest treasure in the cosmos, an ocean of liquid water. A global ocean warmed from below by the planet's own inner turmoil. Here in the crushing pressure and absolute dark, the fury of the star above is a forgotten myth. It has no power here. The only energy, the only light, comes not from a sun, but from the planet's own heart. In these simulations, the seafloor of Proxima b comes alive. Hydrothermal vents driven by the intense geothermal activity pepper the abyssal plain. These are structures that we know intimately on Earth. In our own deep oceans, they are oases of life supporting entire ecosystems that thrive without a single photon of sunlight. Their chemistry, powered by heat and minerals leaching from the planet's crust, is the foundation for a food chain. Could such a scenario exist on Proxima b, a subterranean cradle, protected from the radiation and the temperature extremes of the surface by a thick blanket of ice and rock? Life there would be utterly alien to us. It would have no concept of sight, no sense of day or night. Its entire reality would be defined by pressure chemistry and temperature gradients in the dark. This final possibility is perhaps the most tantalizing because it decouples the question of habitability from the conditions on the surface entirely. It suggests that even the most hellish-looking worlds could be secretly profoundly alive. The planet we see might just be the inert shell for a vibrant hidden biosphere. We could be staring at a living world and not even know it. The implications are staggering. It means our search for life might need to look for more than just the right kind of atmosphere. We might need to look for the subtle geological clues of a planet being tidally heated from within. And so we find ourselves at a crucial turning point. The simple binary question, is Proxima b habitable, yes or no, has dissolved before our eyes. It has been replaced by a far more complex and thrilling tapestry of possibilities. A thick, stormy atmosphere, a tidally forged magnetic shield, a hidden geothermally heated ocean. These are not just wild guesses. They are plausible physical scenarios born from rigorous computer modelling that has fundamentally shifted our understanding. Proxima b is no longer a simple condemned world. It has become a planet of tantalizing what-ifs, a world of extreme niches and potential sanctuaries. The question is no longer a simple matter of survival, but a complex assessment of what minimal conditions, what sliver of opportunity might be enough for life to take hold in the shadow of a violent star. The world next door is not one thing but many. And now we must begin the monumental task of figuring out which of these many faces is the true one, undefined. And so the map is drawn, not of a paradise, but of a possibility, a world of perpetual twilight and searing solar fury, orbiting a star that whispers and rages in the same breath. We have stared into the data, run the simulations, and painted a portrait of Proxima Centauri b. It is a world of extremes, a frontier defined by hardship, a place that might just barely cling to the knife's edge of habitability. But to know a place is not to stand upon it. The gulf between understanding and arrival is the most profound chasm that our species has ever contemplated crossing. 7.5 light years. The distance sounds almost manageable, a single-digit number that belies the true soul-crushing scale of the void. Voyager 1, the fastest object we have ever flung into the interstellar dark, travels at over 38,000 miles per hour. At that speed, a velocity that could cross our entire planet in under an hour, the journey to Proxima b would take over 137,000 years, 137 millennia. An epoch so vast that all of recorded human history, from the first cave paintings to the very moment you are hearing these words, could unfold 13 times over. Our probes would arrive as silent ancient relics, their creators long vanished into the mists of a forgotten past. This is the brutal fundamental truth of the stars. They are not merely distant, they are locked away from us by the physics of our universe, guarded by the tyranny of time itself. To reach them requires not just a faster ship, but an entirely new conception of what a journey can be. It demands a dream, a spark of madness, a willingness to build a vessel not of steel and fire, but of light itself. That dream has a name: Breakthrough Starshot. It is one of humanity's most audacious plans, a breathtaking leap of imagination grounded in plausible near-future technology. The concept is as elegant as it is ambitious. Forget gargantuan starships with crews sleeping for generations. Instead, imagine a fleet of 1,000 tiny probes, each no larger than a postage stamp, a nanocraft, packed with cameras, sensors, and transmitters. Each of these miniature explorers would be attached to a light sail, a gossamer-thin sheet of material just a few meters across, yet more reflective than any mirror ever polished. Here on Earth, deep in a high-altitude desert, we would construct the engine, a phased array of lasers miles wide, capable of combining their power into a single colossal beam. 100 gigawatts of focused energy. For a few terrifying, brilliant minutes, this terrestrial machine would become the most powerful celestial blowtorch in the solar system. This beam, a pillar of pure light, would strike the sails of our fleet. The pressure of photons, the gentle rain of a light that falls on your skin every day, would become a relentless thundering gale. The acceleration would be biblical, from 0 to 100 million miles per hour in minutes. 1,000 gravities of force pushing these tiny emissaries to 20% the speed of light. At such a velocity, the journey of millennia is compressed into a single human generation. The trip to Proxima b would take a little over 30 years. For the first time in history, we can chart a realistic path to sending a piece of ourselves to touch another star system. But the journey through the interstellar medium is not an empty one. Even at a fifth of light speed, a single grain of cosmic dust no bigger than a particle of smoke impacts with the energy of a bomb. Our nanocraft would need to be hardened, shielded, or simply lucky to survive this cosmic hailstorm for 3 decades. And then comes the greatest challenge of all: the arrival. There are no brakes on this ship of light. The flyby would be a frantic, fleeting encounter. Our probes would scream through the Proxima Centauri system in a matter of hours, frantically capturing every photon, every scrap of data before plunging back into the infinite dark on the other side. The information they gather, transmitted back to Earth by a tiny onboard laser, would take another 7.5 years to reach us. A postcard from another world delivered 4 decades after it was sent. Breakthrough Starshot could give us our first close-up look, our first definitive proof of what awaits on Proxima b. But it is a one-way trip for a robot scout, not a bridge for humanity. To carry people, to transport the dreams and futures of a species, we cannot simply be fast. We must be impossible. To build that bridge, we must look beyond conventional propulsion, entirely into the deepest, strangest corners of physics, where the fabric of the universe itself becomes a medium we might learn to command. We must look to the mathematics of a theoretical physicist named Miguel Alcubierre. In 1994, he took Einstein's field equations, the bedrock of our understanding of gravity and space-time, and found something extraordinary hidden within them. A loophole, a way to travel without moving. The Alcubierre drive, or warp drive, and is not a science fiction fantasy. It is a mathematically valid solution to the laws of general relativity. It proposes that a ship wouldn't travel through space, but would instead ride on a wave of space. Imagine you're standing on a rug. To get to the other side, you could walk across it, or you could get the rug itself to move, scrunching it up in front of you and stretching it out behind you, carrying you along with it. The Alcubierre drive is the cosmic version of that rug. A ship encased in a bubble of space-time would compress the fabric of reality in its direction of travel and expand it behind. Inside the bubble, the ship and its crew would be in freefall, experiencing no acceleration, feeling no sense of motion at all. Yet the bubble itself, this distortion in the geometry of the universe, could be propelled forward at speeds far exceeding that of light. The cosmic speed limit would not be broken. It would be sidestepped. It is a ship built of pure mathematics, a ghost in the machine of gravity, the ultimate vessel for plying the stellar seas, and it comes with an impossible price tag. To create such a distortion to bend space-time to your will requires something that may not even exist: exotic matter. Matter with negative mass-negative energy density. A substance that would fall up instead of down, that would weigh less than nothing. It is the theoretical opposite of everything we know and see around us. The energy requirements are also staggering. Early calculations suggested you would need the mass energy of the entire planet Jupiter to power a single small warp bubble. More recent refinements have brought that number down, perhaps, to the mass of a large asteroid, but the challenge remains monumental. We would need to master the creation of matter that defies the known laws of nature and harness energies equivalent to the output of a star. It is a technology so far beyond us that it feels like magic, but the mathematics doesn't lie. The universe allows for it, and if we are to ever become a truly interstellar species, if we are to walk on Proxima b, it is a magic we must learn to master. Let us for a moment perform a miracle. Let us assume that we solve it all, that we either build a ship of light or weave a vessel from space-time and we cross the void. After a journey of decades, or perhaps just weeks, the crimson glare of Proxima Centauri grows from a point of light into a fearsome brooding sun. You arrive. Your ship hangs in orbit over a tidally locked sphere, one hemisphere scorched in perpetual day, the other frozen in unending night. The Terminator zone below that sliver of eternal twilight is a landscape painted in shades of ochre and violet, under a sky thick with a ruddy alien haze. The triumph of arrival, the culmination of humanity's greatest journey, lasts only a moment. It is immediately replaced by the terrifying, all-encompassing task of survival. You have not arrived at a new home. You have arrived at a hostile world that must be completely remade, forged anew in our own image. You have arrived at the anvil of planetary creation, and you are expected to be the hammer. This is the discipline of terraforming the science of world building. And on Proxima b, the task list is daunting. First, the atmosphere. It may be too thin to breathe, too poor in oxygen, or filled with gases poisonous to human life. Creating a breathable atmosphere on a planetary scale is an exercise in controlled celestial violence. We would need to become comet hunters, capturing icy bodies from the outer reaches of the Proxima system and crashing them into the planet's surface. Each impact would be a cataclysm, delivering millions of tons of water vapor, nitrogen, and other vital volatiles. Simultaneously, we would deploy legions of self-replicating robotic factories on the surface, machines designed to consume the native rock and soil, processing it, to release trapped gases, slowly, painstakingly pumping an artificial sky into existence molecule by molecule. This process would take centuries. Generations of colonists would live under domes, watching the atmospheric pressure gauge creep upwards, millibar by agonizing millibar, waiting for the day their descendants could finally breathe the air of their new world. But even a perfect atmosphere is useless if it is simply blown away into space. Proxima Centauri is a flare star. It unleashes sudden, violent bursts of radiation and charged particles orders of magnitude more powerful than those from our own sun. Without a strong global magnetic field like the one that protects Earth, any new atmosphere on Proxima b would be scoured away by these stellar tantrums. The planet's weak or non-existent magnetosphere is its Achilles heel. If the world itself will not provide a shield, we would have to build one. The concept is as audacious as the warp drive. We would need to construct an artificial magnetosphere, a colossal satellite, a superconductor ring kilometers in diameter placed at the L1 Lagrange point, a gravitationally stable spot between the planet and its star. This station would generate an immense magnetic bubble, a protective cocoon that would envelop the entire planet, deflecting the solar wind and shielding the fragile nascent atmosphere below. It would be the single largest and most complex structure ever built by humanity, a silent, invisible guardian against the fury of a red dwarf, an artifact visible not to the eye but to the instruments measuring the flow of cosmic rays, a testament to our refusal to accept the universe as it is given. Only then, after centuries of atmospheric engineering and the construction of a planetary shield, could the final, most delicate work begin. The seeding of life. You cannot simply plant an oak tree and expect it to grow. You must start at the beginning. The first colonists would not be people but microbes. Fleets of probes would dust the planet with genetically engineered extremophiles, bacteria and archaea designed to thrive in the alien soil and low light. These microscopic pioneers would begin the slow, laborious process of biogeochemical transformation. For thousands of years, they would work converting atmospheric carbon dioxide into oxygen, fixing nitrogen into the soil, creating the foundational chemistry for a biosphere. After millennia, perhaps the first lichens and mosses could be introduced, then hardy grasses, then shrubs, and finally, after an epoch that would make all of human civilization seem like a fleeting dream, a forest might grow in the eternal twilight of Proxima b. To terraform a world is to conduct a planetary symphony, with movements that last for centuries, with instruments of cometary impacts and microbial respiration, all building towards a crescendo of a single clean breath taken under an open alien sky. It is the ultimate expression of our desire to make the universe our home. But what if this grand project, this symphony of creation, is too slow? What if the challenges are too great? The timescales too vast for a fragile species accustomed to instant results? There is another path, a more intimate, more disturbing, and perhaps more powerful solution. If we cannot change the world to suit us, perhaps we should change ourselves to suit the world. This is the frontier of transhumanism, the point where biology becomes technology, where human evolution is no longer left to chance, but becomes a matter of conscious design. For a life on Proxima b, the upgrades would need to be profound. Our eyes evolved for the bright yellow-white light of a G-type star, ill-suited for the dim ruddy glow of a red dwarf. Genetic modification, or cybernetic enhancements, could grant us vision tuned to the infrared spectrum, allowing us to see warmth as light navigating the twilight landscape with a clarity no natural human has ever known. The constant bombardment of radiation, even with a partial shield, would be a deadly threat. We could rewrite our own DNA, incorporating genes from radiation-resistant organisms like the tardigrade, making our very cells capable of repairing the damage caused by stellar flares. Or perhaps we integrate nanomachines into our bloodstream, microscopic surgeons that constantly patrol our bodies, fixing broken chromosomes and hunting down cancerous cells before they can form. The slightly higher gravity could be countered with reinforced skeletal structures, the different atmospheric composition with enhanced respiratory systems. We could engineer ourselves to need less oxygen, to be more resilient, to be stronger, to be something new. This path offers a shortcut to survival, a way to inhabit the world as it is not as we wish it to be. But it forces upon us a question that cuts to the very core of our identity. At what point do the alterations become so profound that we cease to be human? The first child born with eyes that see in the dark, with cells that defy radiation, would be the first true native of Proxima b, a new branch on the hominid family tree. The psychological toll would be just as transformative. Imagine living your entire life under a sky that never changes. No sunrise, no sunset. Just a constant dim red glow from a star that hangs motionless in the sky. The familiar rhythm of day and night, a cycle that has governed all life on Earth for billions of years, would be gone. How would this eternal twilight shape the mind, the culture, the art, the religion of a new human society? The very concept of a day would be an ancestral myth. These colonists would be separated from Earth not just by an ocean of space, but by a gulf of experience so fundamental it is almost impossible for us to comprehend. They would be the children of the twilight, forever adapted to a world that their Earthborn ancestors could only visit as fragile, unmodified tourists. This is the ultimate choice we would face: to spend 10,000 years changing the planet, or to spend 100 years changing ourselves. And beneath all of these monumental technical and biological questions, there lies a deeper, more troubling one: the ethical dilemma. In our quest to find a new home, in our desperation to survive, do we have the right to seize a world and utterly remake it? We operate under the assumption that Proxima b is sterile, a blank canvas upon which we can paint our own biological masterpiece. But what if we are wrong? What if deep beneath the regolith, or in some sheltered pocket of liquid water, life has already taken hold? It would likely be microbial, simple, a faint whisper of biology in an otherwise silent system. It would be alien life, the single most profound discovery in human history. And the first act of our arrival would be to extinguish it. Our terraforming efforts, the introduction of our own voracious earthly microbes, would be an act of planetary-scale genocide. We would be wiping out the only other known example of life in the universe to make way for our own. Is any world truly ours to take? Even if it is barren, the act of terraforming is one of supreme arrogance. We would be imposing our biology, our needs, our very definition of life, onto a pristine corner of the cosmos. We would be erasing a unique geological and chemical history that has unfolded over billions of years simply because it was inconvenient for us. The decision to travel to Proxima b to live there is not just a test of our technology, it is a test of our wisdom. It forces us to confront the kind of species we want to be. Are we conquerors reshaping the galaxy in our image, or are we custodians, observers, and humble explorers content to visit, to learn, and to leave the universe's wonders untouched? The journey to Proxima b, it seems, is not just a journey outward into space. It is a journey inward into the very heart of what it means to be human. Perhaps then the immense, seemingly insurmountable challenges of reaching and inhabiting this world are not a cosmic cruelty, but a form of cosmic grace. They give us time to grow, time to mature, time to debate these questions before we develop the power to render them moot. Proxima b hangs in the darkness, a destination, a challenge, and most of all a mirror, and what we see in its faint crimson light will tell us more about ourselves than it ever will about the stars. And so, after decades of travel cocooned in the silent hum of your starship, the dream solidifies into a world of crimson and shadow. Proxima Centauri b hangs before your viewport not as a point of data or a remote spectral analysis, but as a place. A real physical sphere of rock and possibility bathed in the unending, moody glow of its parent star. From this vantage point, the theories and models we explored are laid bare in a geography of brutal contrasts. You see the dayside, a permanent furnace locked in a gravitational shackle, its surface a tortured, hazy landscape shimmering under a sun that never sets. Its reddish light is so intense, so omnipresent, that it likely boils away any chance for liquid water, sterilizing the very rock it was meant to warm. Then, with a slow rotation of your vessel, you witness the night side, an empire of absolute cold, an abyss of frozen gases where the temperature plummets to hundreds of degrees below zero. This is a realm of eternal darkness, a continent of ice that has not felt the direct warmth of its star in billions of years. But between these two impossible extremes there is a third reality, a sliver of hope painted across the circumference of the world, the Terminator Zone. It is a perpetual twilight, a ribbon of dusk and dawn where the searing heat of the day bleeds into the cryogenic cold of the night. From orbit it appears as a soft bruised purple, a delicate transition between fire and ice, and it is here in this sliver of cosmic compromise that the entire story of humanity's future might be written. Your ship's long-range sensors, 1,000 times more sophisticated than any we could launch from Earth, confirm the earlier probe data. A thick atmosphere, far denser than our own, clings to the planet, a crucial shield against the star's violent outbursts, and a blanket to redistribute a meagre amount of heat. It's this atmosphere that creates the weather. On the dayside, superheated gases rise in colossal plumes, driving winds that scream across the planet at hundreds of miles per hour. As they reach the terminator, they cool and descend, creating a storm system of unimaginable and permanent scale. This is no terrestrial hurricane. It is a planetary engine of wind and rain, a perpetual tempest raging along the twilight zone. The dream of colonization is about to collide with a very harsh awakening. The central question, the one that propelled this mission across trillions of miles now, hangs in the silent cabin with an almost physical weight. Could you truly live here? The first landing is not made with a human foot. That would be an act of suicide. Instead, it is a baptism by proxy. From the orbiting mothership, the Odyssey, you and the crew deploy the Sentinel's robotic avatars designed to withstand what a human body cannot. They descend through the turbulent atmosphere, their ceramic shields glowing as they punch through the violent winds of the Terminator. On your screen you see what they see. The sky is not blue or even the familiar orange of a sunset on Mars. It is a deep permanent violet, a bruised purple overhead, filtered through an atmosphere rich in nitrogen, and perhaps argon, but with a chemical signature that is profoundly alien. The light is dim, equivalent to the final minutes after sunset on Earth, but it is a twilight that will never end. The landscape that resolves into view is one of savage grandeur. Mountains crushed and flattened by the high, gravity rise like jagged black teeth against the violet sky. Their slopes are scoured clean by the relentless winds, revealing rock formations in shades of dark red and grey. There is no green. Not a hint of chlorophyll, no sign of the sprawling biomes that so define our own world. This is a mineral kingdom raw and geologically active. One of the Sentinels touches down its heavy legs, absorbing the impact. The gravity here, 30% stronger than Earth's, is an immediate and oppressive force. The Avatar's movements, though powerful, seem laboured. Every action requires more energy. Its external microphones transmit the first sounds of Proxima b. It is not silence. It is the deep, mournful howl of the wind, a constant bass-heavy moan that speaks of a world in permanent atmospheric turmoil. There's also a faint, persistent crackle, the sound of charged particles from Proxima Centauri's frequent flares, interacting with the upper atmosphere, a cosmic static that never ceases. This is the planet's unsettling lullaby. The robot extends a drill, boring into the reddish soil. The analysis comes back in minutes. The regolith is rich in iron oxides, the source of the planet's pervasive dark red hue, but it also contains silicates and heavy metals, the raw materials for a future civilization. Most importantly, deep beneath the surface, protected from the low-level radiation that constantly bombards the planet, the instruments detect water ice. Not vast oceans, but significant subterranean deposits locked away in the permafrost of the colder edges of the Terminator Zone. It is the single most important discovery of the mission. Water is life, but here it is also a shield, a coolant, and a source of fuel. The raw ingredients are here. The potential for a foothold exists, but it will be a fortress, not a home. The site for the first settlement, Elysium Base, is chosen with painstaking care. Not on an open plain where the winds could tear any structure apart, but at the base of a massive gravity-flattened mountain range that can serve as a natural windbreak. The initial construction is entirely automated, a symphony of advanced robotics. Massive borer machines deployed from the Odyssey begin to tunnel into the side of the mountain, carving out the vast caverns that will become humanity's first interstellar outpost. This is not about building domes on the surface. That would be a fragile romantic folly. Survival here means going underground. The native rock itself becomes the primary shield, its thickness absorbing the punishing radiation from the red dwarf star. For months the robots toil, melting the Proxima rock with plasma torches and reshaping it into reinforced structural walls. Large-scale 3D printers using the iron-rich regolith as their feedstock fabricate internal components, interlocking blocks that form habitation modules, laboratories and hydroponic farms. This is a self-sufficient ecosystem in the making, powered by the next generation of compact fusion reactors, their steady thrum the artificial heartbeat of the nascent colony. Every system is a closed loop, a masterpiece of environmental engineering. Air is scrubbed and recycled with near-perfect efficiency. Water from the subterranean ice is purified and reused, with not a single drop wasted. Waste itself is deconstructed at a molecular level, its base elements repurposed as nutrients for the crops that will grow under brilliant full-spectrum LED lights. These farms are the colony's lungs and its stomach. Vast caverns are filled with tiered racks of genetically engineered crops designed to thrive in this artificial environment. They are more than just food. They are an island of familiar green in an infinite landscape of red and purple rock. Their photosynthesis will be a vital supplement to the life support systems, a biological engine working in tandem with the mechanical one. Only when this subterranean fortress is complete, when its fusion heart is stable, and its recycled air is pure, do the first humans descend. Leaving the zero-gravity sanctuary of the Odyssey is a shock. For the first time you feel the planet's true nature not through a screen but in your own bones. The 1.3 Gs are relentless. Your body, which felt light and agile on the ship, now feels heavy leaden. Walking is a conscious effort. Climbing a simple flight of stairs leaves you breathless. Your heart must work significantly harder to pump blood against the stronger pull, placing a permanent strain on your entire cardiovascular system. Your inner ear struggles to recalibrate, leading to a persistent feeling of vertigo. This is a world that is actively trying to pull you down, to crush you under its immense invisible weight. Life inside Elysium Base is a paradox. You're surrounded by the most advanced technology ever created, a testament to human ingenuity, yet your existence is circumscribed, confined to these artificially lit caverns. There are no windows to the outside world. Instead, high-resolution screens project a live feed of the alien landscape, a constant reminder of the beautiful lethal environment just beyond the walls. The sky on these screens is always the same shade of twilight purple, the sun forever hanging at the horizon motionless. There is no day, there is no night. There are only the cycles of the station's clocks, the shifting from work periods to rest periods, marked by a subtle dimming of the overhead lights. This temporal monotony begins to weigh on the human psyche. The circadian rhythms that have governed life for millions of years on Earth are gone, replaced by an artificial, unyielding schedule. Depression and anxiety become as much a medical concern as bone density loss or muscle atrophy. The colonists, the first generation of true Proximans, are pioneers living at the very edge of human endurance. Their children born in the base's medical bay will be a new kind of human. They will take their first steps under a gravity that would feel crushing to an Earth-born child. Their bones will grow thicker, their hearts and muscles stronger, simply to cope with the daily reality of their world. They will never know the feeling of a gentle breeze, only the simulated air currents of the base's ventilation systems. They will never see a blue sky or a yellow sun, only the violet glow on the screens that serve as their windows. Their entire sensory experience, their very definition of normal, will be forged in this alien place. The stories of Earth passed down from their parents will sound like fantastical myths, a world with a light sun, a vast open sky that changes colour, and a gravity that allows you to leap and run with ease. They are native to Proxima b, yet they cannot even set foot on its surface without a heavily armoured excursion suit. This creates a profound and tragic irony. They are the first inhabitants of a new world, and simultaneously prisoners within their own sanctuary. The dream of expansion, of building new cities across the Terminator Zone, remains just that, a dream. The radiation, the winds, and the gravity make surface life as we know it impossible. Humanity has crossed the interstellar gulf only to find itself confined to a gilded cage carved from alien rock. This realization leads the colony to its most daunting and controversial crossroad. Survival is one thing, thriving is another. If humanity is to have a true future on Proxima b, if they are to ever walk under its purple sky without a suit, the problem is not the planet. The problem is us. Our biology, so perfectly adapted for Earth, is the fundamental limitation. And so begins the most ambitious and terrifying project in human history, an endeavour that makes the Starship journey seem simple, by comparison the deliberate guided evolution of the human species. It is a step taken not out of hubris, but out of desperation. The colony's bioengineers, using the advanced genetic tools that were perfected in the decades before the mission, begin to map out a new human genome. The goal is not to create superhumans, but survivors. The first changes are subtle, focused on resilience. They introduce genes borrowed from radiation-resistant organisms on Earth, like the tardigrade to enhance cellular repair mechanisms. This would allow future generations to better withstand the constant bombardment of energetic particles from the red dwarf star. Next, they tackle the crushing gravity. They design genetic modifications to promote denser bone growth to strengthen cardiovascular tissues and to increase the efficiency of muscle fibers. The children of these future generations would be shorter, stockier, more powerfully built a morphology dictated by the laws of physics on their new world. The ethical debates are fierce and agonizing. Back on Earth, 7.5 light-years away, news of the adaptation project is met with a mixture of horror and fascination. Humanity watches with a 15-year round-trip communication delay as their interstellar descendants prepare to redefine the very meaning of being human. The colonists argue that this is no different from vaccination or surgery. It is simply using technology to overcome a hostile environment. But the line they are preparing to cross is a profound one. They are not just curing disease, they are rewriting their own nature. The most radical proposal involves the senses themselves. Proxima Centauri emits most of its energy in the infrared spectrum. To a human eye, the light is dim, the colours muted. But what if you could see in infrared? The engineers propose modifications to the retina, introducing new proteins that would allow future Proximans to perceive heat as light. For them, the world would not be a dim, shadowy place. It would be a vibrant landscape of thermal signatures. Warm geological vents would glow in the distance. Living organisms, if any were ever discovered, would be beacons of light. They would see their world in a way no Earth human ever could. They would be more adapted to Proxima b, but in doing so, they would become irrevocably different from us. A visit to Earth would become a journey to a hostile world for them. Our gentle gravity would feel unnervingly weak, our bright yellow sun a blinding, painful glare. They would be aliens on the planet of their ancestors. So we finally arrive at the answer to our question. Could you live on Proxima Centauri b? The truth is both yes and no. The human being that left Earth, the person you are right now, could not. You could survive for a time sealed inside a subterranean fortress, a visitor in an environment that is fundamentally hostile to your biology. You would be an astronaut on an eternal spacewalk forever separated from the world outside by layers of technology. But your descendants could. They could live there after a profound and irreversible transformation, a journey not of miles but of genes. They would be the children of Proxima, their bodies and senses tuned to the rhythm of a tidally locked world and a violent red star. The price of interstellar colonization, the true cost of becoming a multiplanetary species, is not measured in resources or engineering challenges. It is measured in identity. To conquer a new world, we might have to sacrifice a part of what makes us human. We would have to allow our children to become something new, something other. This is the ultimate legacy of the journey to Proxima b. It reveals that the greatest barrier to our expansion into the cosmos is not the vastness of space. It is the fragility and specificity of our own biology. The universe is not waiting for us with open arms. It is waiting for us to change. And as we stand on the precipice of this new era, we must ask ourselves a final haunting question. If our descendants are no longer like us, who then is the alien? And so after our long and perilous journey across the interstellar void, we find ourselves standing on the precipice of a stark and silent world. We have stared into the heart of its star's fury, mapped the ghostly terminator where light and shadow wage an eternal war, and calculated the crushing gravity that would anchor you to its surface. We have sifted through the thin, tortured wisps of its atmosphere, searching for the biosignatures of a living world, only to find the spectral fingerprints of stellar violence. The question that launched our entire odyssey, the simple, hopeful query of, could you live there now, hangs in the air weighted with the gravity of all we have learned. The answer, etched not in stone but in radiation, scorched regolith and frozen nitrogen, is a profound and resounding silence. A silence that speaks volumes. For us, for life as we have ever known it, Proxima Centauri b is not a sanctuary. It is a tomb, a magnificent, desolate monument to the unforgiving nature of the cosmos. But to leave the story there is to misunderstand the very purpose of exploration. Our journey was never merely about finding a second Earth to colonize. It was about confronting the unknown, about holding a mirror up to the universe and seeing what stared back. Let us rewind the tape just for a moment back to before this world had a name, before it was anything more than a phantom. Remember the beginning. For decades, our most powerful instruments watched our stellar next-door neighbour, Proxima Centauri, a dim, temperamental dwarf star largely ignored in the grand cosmic drama. We watched it not for what it was, but for what it might conceal. The search was a masterpiece of patience, an act of scientific faith conducted on a generational timescale. Astronomers were hunting for a ghost, a wobble so infinitesimally small it was like trying to spot a single firefly dancing next to a celestial searchlight from light years away. They were listening for a whisper in a hurricane, a tiny gravitational tug, the faintest of heartbeats from an unseen partner in a silent cosmic dance. For years, the data was noise, a sea of stellar jitters and instrumental quirks. Hope waxed and waned with every new observation run. Many believed it was a fool's errand that such a volatile red dwarf could never host a stable planetary system. Yet the search continued, driven by that most human of impulses, the need to know what lies just over the horizon. And then it happened. Amidst the chaos of the star's own turbulent life, a pattern began to emerge, a signal subtle but persistent, repeating with the metronomic precision of orbital mechanics. It was the signature of gravity, the unmistakable evidence that something massive was circling that angry star. The ghost in the data was real. A world was there. The thrill of that discovery rippled through the scientific community like a shockwave. We had found a planet not in some distant anonymous star system, but right here in our own cosmic backyard. At a mere 7.5 light-years away, you could practically reach out and touch it on a galactic scale. The initial calculations were tantalizing, almost too good to be true. It was a terrestrial world more massive than our own, a super-Earth. Most intoxicating of all, it orbited squarely within its star's habitable zone, that delicate cosmic shoreline where temperatures could theoretically allow liquid water to pool on a planet's surface. For a brief shining moment, the dream of an Earth-like neighbour, a verdant world ripe for exploration, felt not just possible, but probable. We had found the X on the treasure map. The only question left was what kind of treasure it marked. That moment of pure discovery triggered one of the most intense, investigative campaigns in the history of astronomy. We turned the full might of human ingenuity toward that single distant point of light. The James Webb Space Telescope, our great infrared eye in the dark, stared for hundreds of hours, straining to perform a feat of cosmic surgery, to separate the faint reflected light of the planet from the overwhelming glare of its parent star. Ground-based observatories from the high dry deserts of Chile to the volcanic peaks of Hawaii employed adaptive optics that sharpened their vision to an unprecedented degree, piercing through the shimmering veil of our own atmosphere. We were no longer just tracking a wobble. We were trying to read a world's soul from its light. The work was painstaking. We were attempting to analyse the chemical composition of an atmosphere we couldn't even see, a process akin to determining the ingredients of a cake by smelling it from a mile away. Every photon was precious, every spectral line a clue in a mystery 44 trillion miles in the making. The first revelations were staggering. We confirmed its size and mass, solidifying its status as a rocky super-Earth. We locked down its orbit, a breathtakingly swift 11-day year that kept it perilously close to its volatile star. This proximity brought the next crucial piece of the puzzle into focus, the piece that began to transform our idyllic vision into something far more alien. The planet was tidally locked. Imagine that for a moment. One hemisphere trapped in perpetual searing daylight, the other frozen in an endless abyssal night. There is no gentle rhythm of sunrise and sunset on Proxima b. There is only a fixed, eternal state of being a world cleaved in two by its gravitational chains. The dayside, a landscape under the unrelenting gaze of a red sun, would be a furnace, its rock baked and sterilized over billions of years. The nightside, forever turned away from its only source of warmth, would be a cryogenic wasteland colder than any place on Earth, where any remnant of an atmosphere would freeze solid and fall like snow, never to rise again. This single fact, this gravitational enslavement, reshaped our entire understanding. The habitable zone, that once hopeful concept, became a paradox. The planet was in the right place for liquid water, but its physical state created conditions so extreme that water's existence in a stable life-giving ocean became almost impossible to imagine. The dream of a blue and green world began to fade, replaced by a starker palette of scorched crimson and deep frozen black. Any hope for life, we realised, would have to exist in the margins in that sliver of permanent twilight, between the two extremes, the Terminator Zone. A world of eternal sunset where the winds would scream with unimaginable force as they tried to equalise the immense temperature differential between the two hemispheres. Life here would not be a walk in the park, it would be a constant, desperate battle for survival in a realm of perpetual twilight and supersonic gales. But the final devastating blow to our hopes for an earthly twin came not from the planet itself, but from its parent. Proxima Centauri is no calm, nurturing G-type star like our Sun. It is a flare star, a moody, violent red dwarf, prone to unpredictable cataclysmic eruptions of radiation. We watched as it unleashed superflares, bursts of high-energy X-rays and charged particles, hundreds of times more powerful than anything our own Sun produces. These are not gentle solar winds. They are celestial blowtorches capable of stripping a planet's atmosphere away, over cosmic timescales, boiling off its oceans and sterilizing its surface with deadly radiation. Any nascent life clinging to the surface of Proxima b would be scoured away by these periodic blasts of stellar fire. A protective magnetic field far stronger than Earth's would be required to stand a chance, and even then the bombardment would be relentless. Our models, once filled with possibilities, began to converge on a single grim conclusion. The atmosphere, if it ever existed in a thick, life-sustaining form, is likely long gone, blasted into the void. The water, if it ever pooled in shimmering lakes, is either photo-dissociated into space or locked away as subterranean ice on the frozen night side. The surface is a radiation-battered desert. So could you live there? No, not without technology so advanced it borders on magic. You could not breathe the air, you could not drink the water, you could not withstand the gravity, and you certainly could not survive the star. And yet this is not a story of failure. It is a story of profound, necessary revelation. Proxima Centauri b has taught us one of the most important lessons in our search for life beyond Earth. The universe is far more creative and far more brutal than we ever imagined. The concept of a habitable zone has been shown to be a beautiful but dangerously simplistic first guess. Habitability is not just about temperature. It is a complex symphony of countless interconnected variables. It's about the stability of the star, the presence of a global magnetic field, the planet's geological activity, the existence of a large moon to stabilize its axis, the composition of its atmosphere, and a dozen other factors we're only just beginning to appreciate. Proxima b, by failing to be Earth-like, has expanded our imagination. It forces us to ask new, more sophisticated questions. Could life exist not on the surface but deep underground, shielded from the radiation? Could a subsurface ocean warmed by tidal forces and geothermal vents harbour ecosystems entirely divorced from the light of a sun? Could life adapt to conditions we consider unsurvivable, evolving biochemistries that thrive on the edge of a knife? This world, our nearest exoplanetary neighbour, has become the ultimate laboratory for extreme planetary science. It is a whetstone against which we are sharpening our theories of planetary formation and our understanding of the boundaries of life itself. It serves as a critical signpost directing the search for life not just towards gentle Earth-like worlds, but also to the icy moons of our own solar system, to the subsurface oceans of Europa and Enceladus, places that now seem less alien and more plausible as abodes for life. And as we zoom out, Proxima b's true significance comes into focus. It is just one world. The first one we could study in such detail. Its discovery confirms that planets around red dwarfs, the most common type of star in the Milky Way, are ubiquitous. Our galaxy is not empty. It is teeming with worlds. Billions upon billions of them. Most might be hostile like Proxima b. Many might be sterile gas giants or scorched lava planets. But the sheer numbers play a game of cosmic roulette that almost guarantees that somewhere out there in that vast darkness, the right conditions have aligned. Proxima b is not the destination. It is the first step on a galactic breadcrumb trail. It is the proof of concept that worlds are everywhere, and it provides the crucial data we need to refine our search to know what to look for and what to look out for. The next generation of telescopes already on the drawing board will be designed with the lessons of Proxima b in mind. They will be able to untangle the light from more distant worlds to sniff out the atmospheres of true Earth analogues, orbiting calmer, more sun-like stars. Our nearest neighbour has prepared us for the greater journey ahead. It has shown us the difficulty of the road, but it has also confirmed with absolute certainty that there is a road to travel. The search for extraterrestrial life has been transformed from a speculative dream into a data-driven systematic science, and this strange, tidally locked super-Earth next door was the catalyst. Ultimately, though, the greatest lesson from this journey across 7.5 light-years may not be about alien worlds at all, but about our own. In confronting the violent, sterile reality of Proxima b, we are forced to turn our gaze back to the pale blue dot we call home. We leave a world of crushing gravity of relentless radiation of a sky dominated by a swollen, angry red star, and we return here. We return to a world shielded by a miraculously powerful magnetic field, a silent, invisible guardian that deflects the solar winds. We return to a planet with a perfect axial tilt and a 24-hour rotation, a gentle, dependable rhythm that evens out temperatures and drives the cycles of life. We come home to a world with a dynamic, churning core that powers plate tectonics, recycling nutrients, and regulating our climate over geological ages. We come back to an atmosphere thick with oxygen, to vast deep oceans of liquid water, to a sun that warms us with a stable, life-giving light. We have spent this entire journey searching for the conditions for life, only to realise that we have been living inside a paradise all along. Every sunrise, every rainstorm, every breath you take is the result of a chain of cosmic luck so improbable it borders on the miraculous. The things we take for granted, a blue sky, a gentle breeze, the simple feeling of cool water, are from a galactic perspective among the rarest and most precious treasures in the universe. The journey to Proxima Centauri b was never just about finding a new planet. It was about gaining a new perspective. It was about understanding in our bones the sheer fragility of our existence. Earth is not a given. It is not a birthright. It is an anomaly, a precious, delicate oasis of life in a cosmos that is overwhelmingly hostile to it. We look at the scorched Earth of Proxima b, and we see a possible future for any world that loses its atmospheric shield. We see the consequence of a star's fury, and are reminded of our own star's life-sustaining grace. And with that understanding comes a profound and urgent responsibility. The drive to explore, to push our robotic envoys and our telescopes further into the unknown, is one of humanity's noblest qualities. We must continue to look outwards to search for answers to the great questions of our existence. But we must do so with the wisdom that this exploration provides. The knowledge that there is no Planet B, no easy escape hatch, waiting for us just a few light years away should not be a source of despair, but a source of inspiration. It is a call to action. It compels us to cherish, to protect, and to fight for the only truly habitable home we will ever know. Our cosmic neighbour in all its desolate grandeur has given us the greatest gift of all the clarity to see the breathtaking miracle of Earth for what it truly is, and the wisdom to know that its future is, and always has been, entirely in our hands.